Have you ever looked around and wondered how things in nature just find their balance? Well, it's not an accident. Today, we are pulling back the curtain on one of chemistry's biggest ideas, chemical equilibrium. You know, it's this invisible dance that's happening all around us all the time, governing everything from the air we breathe to the food we eat.
So, here's our game plan. First up, we're going to get to the bottom of what dynamic equilibrium really is. Then, we'll check out how chemists actually put a number on it. After that, the fun part. We'll see how we can mess with these systems to get what we want. And to wrap it all up, we'll look at how this one simple idea literally changed the world. Let's dive in.
All right, first things first, the dance of molecules. We're going to figure out what is really going on when it looks like a chemical reaction is just given up and stopped.
You've probably wondered about this, right? You mix some chemicals together, you're expecting this big, complete change, and nothing. It just kind of stops, maybe halfway through. It looks like it's done, but what's happening under the surface is anything but.
And here's the secret. Most chemical reactions aren't a one-way street. They're reversible. It's not just reactants turning into products. Oh no, those new products can actually turn right back around and become the reactants they started as. It's a two-way highway.
Now, this is a really key idea. Usually when we think of balance, we picture something totally still, right? Like a scale. But chemical equilibrium is dynamic. Think about it like a really busy nightclub with two rooms. People are walking back and forth between the rooms all night long, but the number of people in each room pretty much stays the same. That's it. Constant motion, but no overall change.
And that brings us to the textbook definition. Dynamic equilibrium is simply that point where the forward reaction, so reactants making products, is happening at the exact same speed as the reverse reaction. The dance of molecules is just perfectly in sync.
Okay, so if every reaction has this special balance point, how in the world do we know where it is? Well, for that, we need to look at the reaction's rulebook, the equilibrium constant.
This little value, we call it Kc, is basically the reaction's personality score. It tells us, for a specific temperature, what the final score will be, the ratio of products to reactants, once everything is settled down. It lets us put a hard number on that balance point we were just talking about.
And figuring out this Kc value, it's actually way easier than it looks. It's just a simple ratio. You take the concentration of your products, put them on top. Then you take the concentration of your reactants, put them on the bottom. And those little balancing numbers in the chemical equation, they just become powers. That's it. It's a simple formula that tells you who's winning at the end of the day, the products or the reactants.
And the number you get tells you the whole story. If Kc is a huge number, it means the reaction heavily favors the products. It pretty much goes all the way. If Kc is super tiny, the reaction barely even gets started. And if it's somewhere around 1, you've got a healthy mix of both reactants and products hanging out together.
So, knowing where our reaction naturally wants to settle is cool and all, but what if we want to, rig the game? What if we want to force it to make more of what we want? Well, that's where we learn how to push the system's buttons using this awesome idea called Le Chatelier's principle.
Okay, this principle is a total game changer in chemistry. Just think of a system at equilibrium like a person walking a tightrope. If you suddenly push them to the left, what do? They immediately lean to the right to get their balance back. Chemical systems do the exact same thing. They will always fight back against any change or stress you throw at them.
So, what kind of stress are we talking about? Well, the first and probably most obvious one is just changing the amount of one of the chemicals. It's really just like a seesaw. If you dump a bunch more reactants on one side, you're weighing it down. So what does the system do? It shifts to the other side. It makes more products to try and even things out again. And get this, it also means if you keep taking the products away as they're made, the reaction will just keep pushing forward to make more. Pretty clever, huh?
All right, the next button we can push, and this one is mainly for reactions with gases, is pressure. This is all about changing how much elbow room the gas molecules have.
And the way the system deals with this is just brilliant. If you crank up the pressure, you're basically squishing all the molecules together. To ease that stress, the equilibrium will shift toward whichever side of the reaction has fewer gas molecules. I mean, fewer molecules means less crowding, right? It's the system's way of making more space for itself.
And the last major stress we can apply is temperature. The easiest way to think about this is to imagine heat is either a reactant or a product. Some reactions give off heat, and some need to absorb it to happen.
So it follows the same logic.
If you add heat by cranking up the temperature, the equilibrium will shift in the direction that soaks up that extra heat. That's the endothermic direction. And if you cool the system down, it'll shift in the direction that creates heat, the exothermic direction, to try and warm itself back up. It always fights back.
Okay, I know this has all been a bit theoretical, so let's bring it all crashing down to earth with an absolutely incredible real-world example, the Haber-Bosch process. This is the story of how we use equilibrium to literally feed billions of people.
Just look at that number for a second. 150 million tons. That's how much ammonia we make every single year with this process. And pretty much all of it gets turned into the fertilizer that our global food supply depends on. It's honestly one of the most important chemical processes ever invented.
And this is the reaction that makes it all possible. We take nitrogen, which is all around us in the air, and combine it with hydrogen to make ammonia. Now notice two crucial things. You see those double arrows? It's a reversible reaction, so it reaches equilibrium. And you see that plus heat? It's exothermic. It releases heat when it goes forward.
So this is where it all comes together. This is a masterclass in hacking equilibrium. Chemists use crazy high pressures, which forces the reaction to the side with fewer gas molecules. That's the ammonia side. Then they constantly pull the ammonia out of the system, which tricks the reaction into making more and more to replace it. They even play with the temperature. It's a careful balancing act between getting a good yield and getting it fast enough. It is the perfect, real-world recipe using every single principle we just covered.
So you see, understanding equilibrium isn't just about passing a chemistry test. It's a fundamental principle that, once we've figured out how to control it, literally changed the fate of humanity and fed the planet. It really makes you wonder, where else is this invisible balancing act quietly shaping our world right now? That's definitely some food for thought. Thanks for joining me.